In question 1, we're given y here in terms of x, and we need to find in its simplest form dy dx and the 2y by dx squared. Well, we know that in differentiation we get the power down and we deduct 1 from the power, so dy dx here will be equal to 4 times 3x squared minus 7 times 2x plus 5, which simplifies to 12x squared minus 14x plus 5. Now for the second derivative, the 2y by the x squared, we just take the expression we just obtained for dy dx and we differentiate again. So the derivative of 12x squared is going to be 12 times 2x minus 14, which simplifies to 24x minus 14. In part B, we are asked to hence find the exact value of x when the 2y by the x squared is equal to 0. So we're looking at 24x minus 14 is 0. So we've got 24x is 14. And if I divide both sides by 24, we arrive at x being 7 over 12. In question 2, we've got Jamie who takes out an interest-free loan of £8,100. Now he will be making a payment every month to pay back the loan, starting with 400 in month 1, then 390, then 380, and so on, so that the amounts repaid each month form an arithmetic sequence. And we need to show that Jamie will be repaying £290 in month 12. Well, we know that for an arithmetic sequence, the nth term is given by a plus n minus 1d, where a is the first term and d is the common difference. Well, the first term is the 400, so a is equal to 400, and the common difference is negative 10, because successive terms of this sequence differ by 10, so we've got a decrease of 10 every time. This means the common difference is negative 10, and therefore if we're looking for month 12, so in month 12 I will simply substitute n is 12, so we're looking for the 12th term of this sequence, so that's going to be 400 plus 12 minus 1 times the negative 10. This gives an answer of £290 as required. Now after Jamie's nth payment, the loan is completely paid back, and we need to show that this leads to n squared minus 81n plus 1620 is equal to 0. Well, we know that for an arithmetic sequence, the sum of the first n terms is given by n over 2 times 2a plus n minus 1d. Well, we have just been told that S capital N is equal to 8,100 because we are fully repaying the loan, which means that we've got 8,100 being equal to capital N over 2 times 400, which was the A, plus capital N minus 1 times the negative 10. So let's proceed in simplifying things. We've got 8,100 being equal to n over 2, and within the bracket we've got 800 minus 10n plus 10. So we're looking at 8,100 being equal to n over 2 times the 810 minus the 10n. I will expand the right hand side to arrive at 8,100 being equal to 405 capital N minus 5n squared, and I will be collecting everything on the left hand side to give me 5n squared minus 405n plus 8,100 being equal to 0. Now I will divide throughout by 5, arriving at n squared minus 81n plus 1620 is equal to 0 as required. In part C, we're asked to hence find the value of capital N, so I need to solve the given quadratic equation here. One way I can do this is by factorization. It factorizes into n minus 36 times n minus 45 is equal to 0. So we're looking at n minus 36 is 0, or n minus 45 is equal to 0, and therefore we've got solutions of n being 36 or n being 45. Now both of these are solutions to this quadratic, but we only need to pick the earliest solution because the loan will be fully repaid in the first 36 months. There is no reason to wait for 45 months, so I need to conclude that capital N is equal to 36. Now, in case we cannot do the factorization, we could just go on the calculator, we press menu, it's option A, it's a polynomial of degree 2. Now my A is 1, my B is negative 81, and my C is 1620. This will give me the solution straight away. So the first solution is 45, the second solution is 36, and I could simply state that n is 36 to claim the 2 marks here. In question 3, we've got the point P with coordinates 3, negative 2 lying on the curve with equation y is f of x, and we are asked to find the coordinates of the point to which P is mapped when the curve with equation y is f of x is transformed to the equation given here. So we've got 3 transformations. We start with y is f of x minus 2. We're looking at a translation of 2 units to the right. This means that we are adding 2 to x, and therefore the point with coordinates 3, negative 2 will now be found at 5, negative 2. We simply added 2 to x. In II, we're looking at y is f of 2x, so this time we are stretching along the horizontal with a scale factor over half. The 2 here means that all the x values are divided by 2, or simply we are multiplying x by a half, and therefore the point 3, negative 2 will now be found at 3 over 2, negative 2. In III, we've got y is 3f of negative x plus 5, so we've got 3 transformations applied here. The negative x here means we are reflecting along the y-axis, we are multiplying x by negative 1. The 3 here means we are multiplying the y values by 3. It's a stretch along the vertical scale factor of 3. And the plus 5 here is a translation 5 units up, so we are adding 5 to y. And therefore the point 3, negative 2 will see its x coordinate being multiplied by negative 1, so negative 3. And its y coordinate of negative 2 will be multiplied by 3 and then added 5, leading to negative 3, negative 1. In question 4, we've got a sequence defined recursively here. Un plus 1, the next term is k times the previous term minus 5. And we start with the first term being 6. K is a positive constant. And given that the third term is negative 1, we need to show that this leads to 6k squared minus 5k minus 4 is 0. So let's start with u2, which is equal to k times u1 minus 5. Well, we know that u1 is 6, so u2 is 6k minus 5, and we can proceed with u3. So u3 is k times u2 minus 5, and u3 is negative 1, which is k times the 6k minus 5, close brackets, minus 5. So we're looking at negative 1 is 6k squared minus 5k minus 5, which leads to 0 being 6k squared minus 5k minus 4 as required. We are then asked to hence find the value of k and then find the value of the sum of ur from r is 1 up to r is 3. Now for the value of k, obviously I'll be solving the quadratic we obtained in part A. So this quadratic factorizes into 2k plus 1 times 3k minus 4, and this is equal to 0. So we're looking at 2k plus 1 is 0, or alternatively 3k minus 4 is 0. So 2k is negative 1, which means that k is negative a half, or 3k is equal to 4, which means that k is 4 over 3. Now we were told that k is positive, so since k is greater than 0, we conclude that k is equal to 4 over 3. Now for II, we need to find the sum of ur from r is 1 up to r is 3. So we're looking at u1 plus u2 plus u3. Well, we already know that the first term u1 is simply 6. Now u2 was found to be 6k minus 5, so 6 times 4 over 3 minus 5, which gives a result of 3, and we know that u3 is negative 1, and therefore the sum of ur from r equals 1 up to 3 is simply going to be u1 plus u2 plus u3, which is equal to 6 plus 3 plus the negative 1, which gives an answer of 8. Question 5 is on the small angle approximations. We are told that theta is small and in radians, and we need to use the small angle approximations to find the approximate numerical value of theta tan 2 theta over 1 minus cos 3 theta. Well, let's start by recalling that the small angle approximations state that if theta is small and in radians, then sine of theta is approximately theta, cos of theta is approximately 1 minus theta squared over 2, and tan theta is approximately theta. So theta tan 2 theta over 1 minus cos 3 theta will be approximately theta. Now the tan 2 theta will be approximately 2 theta, and the 1 minus cos 3 theta will be approximately 1 minus, and I've got 1 minus the 3 theta squared divided by 2. Now let's simplify this. We are looking at 2 theta squared over 1 minus 1 minus 9 theta squared over 2. I will proceed in simplifying. We've got 2 theta squared in the numerator, and in the denominator we've got 1 minus 1 plus 9 theta squared over 2. Obviously the 1 with the negative 1 will cancel out. The theta squared with the theta squared will cancel out. And 2 divided by 9 over 2 gives an answer of 4 over 9, which is the final answer. In question 6, we are given a sketch of the curves with equations y is f of x and g of x given here. In part A, we need to find f dash of x and g dash of x. So f of x is e to the 4x squared minus 1. So to find f dash of x, I will start by differentiating the 4x squared minus 1, which gives me 8x. So it's 8x e to the 4x squared minus 1. And for the g dash of x, well, the derivative of 8 ln x, it's 8 times the derivative of ln x, which is 1 over x. So we're looking at 8 over x. We then have that f dash of x is equal to g dash of x at x is alpha, and we need to show that alpha satisfies the equation shown here. So let's start by equating the two derivatives. We're looking at 8x e to the 4x squared minus 1 being equal to 8 over x. The first thing to do is simplify out the 8's on either side, and then we're looking at e to the 4x squared minus 1 being equal to 1 over x squared. So I simply divided both sides by x. So I will proceed by writing 1 over x squared as x to the negative 2, and I will take ln of both sides, taking me to 4x squared minus 1 being equal to ln of x to the negative 2. Now obviously the negative 2 being a power here can come down, so we've got 4x squared minus 1 is equal to minus 2 ln x, and I can collect everything on the left hand side to arrive at 4x squared plus 2 ln x minus 1 is 0 as required. We are then given this iterative formula, and we are starting with x1 is 0.6, and we need to calculate to 4 decimal places the value of the next iteration x2, and then the value of alpha, the solution to the equation f dash of x is g dash of x. So I will do this on the calculator. So I go on the calculator, I press 0.6 and I store it on my answer key, and then I'll be doing square root of 1 minus 2 ln of the answer, and all divided by 4. So each time I press the equals button, I get the new iteration. So we are starting with x1 being equal to 0.6. I will now press the equal button. We get the next iteration. It's 0.7109. And if I keep pressing the equal sign here, I've got new iterations coming over, and eventually we can see that we stabilize. We can see it's 0.67, and eventually it will stabilize. We can see that the first 4 decimal places are 0.6706, and therefore we conclude that alpha is 0.6706. Question 7 is on vectors. We've got a sketch of the straight line L here. Now this line is passing through the points A and B. We've got the position vector of A and the position vector of B, and we need to find the vector AB. Well, we know that to go from A to B, I do the position vector of the second letter, so OB, minus the position vector of the first letter, so OA. So we're looking at 5I plus 6J plus 8K minus the position vector of A, which was 2I minus 3J plus 5K. Now 5 minus 2 is 3, so the answer is 3I. Then we've got 6J minus the negative 3J, so plus 9J. And then we've got 8 minus the 5K, so 8 minus 5 is 3, so plus 3K. So AB is 3I plus 9J plus 3K. We're then told that there's a point P lying on L such that the distance AP is twice the distance BP, and we need to find the possible position vectors of P. So looking at the diagram, we've got two cases to consider. The first case that P lies between A and B, so that the distance AP is twice the distance PB, which means that P is splitting AB in the ratio 2:1. So AP is 2/3 of AB and PB is 1/3 of AB. Or alternatively, P is further along the line somewhere here, so that AP here is twice the distance BP. So these are the two scenarios I need to consider. So for the first scenario, we're trying to find OP, which I will write as OA plus AP. So I'm simply saying that to go from O to P, I will go from O to A and then from A to P. Now OA is the vector 2, -3, 5, and then to go from A to P, I will simply do 2/3 of AB, so plus 2/3 of AB. So we're looking at 2, -3, 5, plus 2/3 of the answer we obtained in part A, which was 3, 9, 3. So we're looking at 2, -3, 5. Now 2/3 of 3 is 2, 2/3 of 9 is 6, and then again 2. So this gives an answer of 4, 3, 7. For the second case, I will start again saying that OP is simply OA plus AP. Well, we've got OA to be 2, -3, 5, and we can see that in this case AP is simply 2 times AB, so plus 2AB. So we've got 2, -3, 5 plus 2 times the 3, 9, 3, which gives me 2, -3, 5 plus 6, 18, 6, which of course simplifies to 8, 15, 11. That's the second possible position vector for point P. In question 8, we need to show all stages of our working, and solutions relying entirely on calculator technology are not acceptable. So in the first part, we need to prove that 1 over cosec theta minus 1 plus 1 over cosec theta plus 1 is 2 tan theta sec theta. So we need to prove this trigonometric identity. I will start from the left-hand side. I'll be expressing everything as a single fraction with the denominator of the LCM, which is cosec theta minus 1 times cosec theta plus 1. So looking at the first fraction we had here, I need to multiply this by cosec theta plus 1, and the second fraction by cosec theta minus 1. So in the numerator, we're looking at 2 cosec theta, and I will be expanding the denominator to get cosec squared theta minus 1. Well, we should be able to recognize the cosec squared theta minus 1 as being cot squared theta, and this means that we're looking at 2 cosec theta and all divided by cot squared theta. So what I'm going to do now is that I'm going to write the cosec theta as 1 over sine theta, and then the cot squared theta is cos squared theta over sine squared theta, and I will simplify this, Remember, we're trying to arrive at 2 tan theta sec theta. So I'll be multiplying 1 with sine squared and sine with cos squared. So we've got 2, and I've got the sine squared theta. And in the denominator, we've got sine theta cos squared theta. Obviously, the sine square with the sine theta simplify, and I'm left with 2 sine theta over cos squared theta, which I can write as 2 times 1 over cos theta times sine theta over cos theta. So all in all, we're looking at 2 sec theta tan theta, which is equal to the right hand side as required. In part B, we need to hence solve for x between 0 and 90 degrees. The given equation here, giving each answer in degrees to 1 decimal place. Well, I recognize the left-hand side as being the identity we just proved, with theta being replaced with 2x. So the left-hand side is simply 2 tan of 2x sec of 2x. And on the right-hand side, we've got cot of 2x sec of 2x. So I will write everything in terms of sines and cosines. So we've got 2 sine of 2x over cos 2x, that's the tan 2x, times 1 over cos of 2x is equal to cos of 2x over sine of 2x times 1 over cos of 2x. Now we can see that the cos of 2x will cancel out. So we're looking at 2 sine of 2x over cos squared 2x being equal to 1 over sine of 2x. I will cross multiply to get 2 sine squared 2x being equal to cos squared 2x. And I will then proceed by dividing both sides by cos squared 2x. This will give me a tan squared 2x term on the left hand side. So we're looking at 2 tan squared of 2x being equal to 1, and therefore tan squared of 2x is equal to a half. I will proceed by taking the square root of the half. So we either have tan of 2x being equal to the square root of 1 over 2, or alternatively, we've got tan of 2x being equal to the negative square root of 1 over 2. I will proceed by finding the principal value. So the PV here is going to be shift tan of the square root of 1 over 2. I'm going to go on my calculator, shift tan of the square root of 1 over 2 gives an answer of 35.264. So I write the PV here to be 35.264 ... and I will be storing this value on A. So the A key here is holding the exact value. And we know that when we are solving trigonometric equations involving tan, the solutions are given by the PV plus 180k. So in this case, 2x is equal to A plus 180k. And if I divide throughout by 2, we get that x is A plus 180k divided by 2. And then moving over to the tan of 2x being negative, the square root of 1 over 2. Let's find the PV, which is going to be shift tan of the negative square root of 1 over 2. So shift tan of minus the square root of 1 over 2 gives an answer of negative 35.264 ... I will store this on B. So the B button is holding this principal value, and we therefore have 2x is equal to B plus 180k, and this leads to x being B plus 180k and all divided by 2. I can therefore go on the calculator, press menu, option 9. My f of x is going to be the A plus the 180 x divided by 2. So let me write the x here. So we've got 180x divided by 2. I press the equal sign. My g of x is going to be the B plus the 180x divided by 2. I will start at -2. I will go up to 5. I'm stepping everyone. Essentially, I'm automating the whole process of generating solutions. Remember, x is between 0 and 90. So let's see the solutions here. The first solution between 0 and 90 is the 17.6. So let me write this here. X is 17.6. And another solution is the 72.4. So a total of 2 solutions for this trigonometric equation. In question 9, we've got the graph here showing the path of a small ball. Now this ball is traveling in a vertical plane above horizontal ground, and the ball is thrown from the point represented by A with coordinates 0, 2, and is caught at the point represented by B with coordinates 20, 0.8. Now the distance capital H meters above ground has been plotted against the horizontal distance x meters, and we are told the coordinates of A and B. We are additionally given that the ball attains its maximum height when x is 9, and we need to find a quadratic function that links capital H with x. So we've got the maximum point here when x is 9. So we're looking at a quadratic relationship between capital H and x, and based on the fact that the maximum is attained when x is 9, then we are proposing that the form of H in terms of x will be one of capital H being alpha x minus 9 squared plus beta. We need to find the constants alpha and beta. Now this particular form is ensuring that when x is 9, we've got the turning point because this bracket becomes 0. And I will then proceed by saying that when x is 0, we know that capital H is 2. So let me substitute this. We get 2 is equal to alpha 0 minus 9 squared plus beta, taking me to 2 is equal to 81 alpha plus beta. And then based on the coordinates of B, we know that when x is 20, capital H is 0.8. So this means that 0.8 is equal to alpha 20 minus 9 squared plus beta. So we've got 0.8 being equal to 121 alpha plus beta. So I simply need to solve simultaneously the two equations. Let me write one below the other. So we've got 2 is equal to 81 alpha plus beta. I will be deducting one from the other, taking me to negative 1.2 being equal to 40 alpha. And if I divide both sides by 40, we get that negative 0.03 is the value of alpha. Well, I was expecting the alpha to be negative because we should be looking at the sad phase parabola. So the coefficient outside the bracket should be negative. And then I need to proceed to find the value of beta. So we know that 2 is 81 alpha plus beta. So 2 is equal to 81 times the negative 0.03 plus beta, taking me to 2 is equal to minus 2.43 plus beta, and therefore 4.43 is the value of beta. And to claim all marks, I need to state the equation of the model with alpha and beta being substituted with the values we just obtained, and therefore we conclude that capital H is negative 0.03 x minus 9 squared plus the 4.43. Now an alternative approach would be to start by a very general form for the quadratic. So H is alpha x squared plus beta x plus gamma. Well, we know that when x is 0, capital H is 2, and this means that 2 is equal to gamma because these two terms will be 0. I can then use the fact that when x is 20, we've got capital H to be 0.8, which means that 0.8 is equal to alpha times 20 squared plus beta times 20 plus the value of gamma, which we found to be 2. I'll be moving the 2 over the left-hand side, taking me to negative 1.2 is equal to 400 alpha plus 20 beta. And then I'll be using the fact that we attain the maximum when x is 9. This simply means that dh dx evaluated at x is equal to 9 should give me a result of 0, because when x is 9, we've got a turning point. Now I can take this equation here and differentiate. So dh by dx is equal to 2 alpha x plus beta. I will evaluate this when x is 9. So dh dx when x is 9 is equal to 2 alpha times 9 plus beta. So we're looking at 18 alpha plus beta, which we know should be equal to 0. And this simply means that beta is negative 18 alpha. So again, I'm dealing with simultaneous equations. I'll be substituting beta is negative 18 alpha into this equation here to get the value of alpha and then proceed with beta. So we've got negative 1.2 being equal to 400 alpha plus 20 times the negative 18 alpha. So negative 1.2 is 400 alpha minus 360 alpha, and therefore negative 1.2 is 40 alpha. I'll divide by 40 to get the negative 0.03 to be the value of alpha, and then beta is just negative 18 times alpha, so negative 18 times the negative 0.03, which gives an answer of 0.54. And then we conclude that capital H is negative 0.03x squared plus 0.54x plus 2, which again is a perfectly acceptable answer for the first part of this question. In part B, we need to give one limitation of the model, and there are several points we could raise here. One of them is that the model is not allowing for any obstacles in the path of the ball. We could mention that the ground is unlikely to be horizontal, or even mention that air resistance has not been considered. Now Chandra is standing directly under the path of the ball at a point 16 meters horizontally from O. Now she can catch the ball if it's less than 2.5 meters above ground, and we need to use the model to determine if she can catch the ball. So this is the situation here. We've got the maximum we said at 9. We've got the expression for capital H in terms of x. Now Chandra is standing exactly at this point here, and we need to determine the height. If this height turns out to be less than 2.5 meters, then we can conclude that she can catch the ball. So we simply need to evaluate capital H when x is 16. So let me write down here when x is 16. We've got capital H being negative 0.03 times 16 minus 9 squared plus the 4.43. This gives an answer of 2.96, which is greater than 2.5. And therefore we conclude that Chandra cannot catch the ball. Question 10 is on parametric equations. We've got the curve here C with parametric equations x is t plus 3 all squared and y is 1 minus t cubed. Now the parameter t varies between negative 2 and 1 inclusive. We are told that the point P with coordinates 4, 2 lies on C, and we need to use parametric differentiation to show that the tangent to C at P has equation 3x plus 4y is 20. Well, the first thing to do is determine the corresponding value of t, the parameter t, at the point P with coordinates 4, 2. So I can simply say that when y is equal to 2, we're looking at 2 being equal to 1 minus t cubed. So t cubed is equal to negative 1, and therefore t is the third root of negative 1, which is negative 1. I've got the value of the parameter. I will proceed by finding dx dt and dy dt. So for dx dt, we simply have 2 times t plus 3. So I got the power down. I deducted 1 from the power times the derivative of the bracket, which is simply 1. And then for dy by dt, we simply got this to be equal to negative 3t squared. And then we proceed with dy dx, which we know to be equal to dy by dt over dx by dt. So this is equal to negative 3t squared over 2 times the t plus 3. I will proceed by evaluating dy dx when the parameter t is equal to -1. This will give me the gradient of the tangent. So we're looking at -3 times -1 squared over 2 times the -1 plus 3. This gives an answer of -3 over 4, which is the gradient of the tangent. And therefore I can proceed with y minus y1 is mx minus x1 to get that y minus 2 is equal to -3 over 4 brackets x minus 4. I will cross multiply to get 4y minus 8 is equal to -3x plus 12, and therefore we arrive at 3x plus 4y is equal to 20 as required. Now the curve C is used to model the profile of a slide at a water park. Units are in meters, with y being the height of the slide above water level, and we need to find, according to the model, the greatest height of the slide above the water level. So let's recall the graph that we were given. We've got the equations for x, y, we've got the range of values of t here. Now obviously the maximum height is over here at the beginning. We can see that y is a maximum when t is -2, because -2 to the power of 3 will be -8, and then I'll be doing 1 minus the -8 to get this maximum. So I will simply say that when t is equal to -2, we get that y is 1 minus the -2 cubed, which gives an answer of 9. And to claim these marks, since this is a modeling question, I need to include units. Therefore, the greatest height above water level is found to be 9 meters. In question 11, we need to show all stages of our working, and solutions relying entirely on calculator technology are not acceptable, so we need to be careful here to show our working clearly. Now we've got a sketch of part of the curve with this equation here, and the finite region R shown shaded here is bounded by the curve above, the x-axis, and the line x is equal to 1, and we are asked to determine the exact area of R, giving our answer in the form a plus b e to the -3, where a and b are rational numbers to be found. So I'll be using integration to find the area R. I'll be integrating y with respect to x, and to do that I will be using integration by parts. So let's recall that in integration by parts, the integral of uv dash is uv minus the integral of u dash v. So first of all, let's write down that the region R is given by the integral from 0 up to 1 of 8x squared e to the -3x dx. So my u is gonna be the 8x squared, and my v dash is gonna be the e to the -3x. This means that u dash is 16x, and v, I will simply integrate e to the -3x, giving an answer of -1/3 e to the -3x. So the integral of 8x squared e to the -3x dx is given by 8x squared times the -1/3 e to the -3x minus the integral of 16x times -1/3 e to the -3x dx. I'm omitting the limits for the time being. I'm just concentrating on doing the integration. Now, this part here does not involve an integral, so we're looking at -8 over 3x squared e to the -3x. And now the negative with this negative will make a positive, so we're looking at plus the integral of 16 over 3x e to the -3x dx. So we've got something simpler to integrate here, because originally we had the product of a quadratic with an exponential term. Now it's a linear term with an exponential term, but I still need to apply integration by parts a second time for this integral here. So let's consider the integral of 16x over 3 e to the -3x dx. So I'll be setting u to be 16x over 3 and v dash to be e to the -3x. This means that u dash is 16 over 3, and then v is -1/3 e to the -3x. So this integral here is going to be 16x over 3 times minus a third e to the minus 3x minus the integral of 16 over 3 times minus a third e to the minus 3x dx. So this simplifies to minus 16x over 9 e to the minus 3x. And now this minus with this minus will give me a positive. So we're looking at plus the integral of 16 over 9 e to the minus 3x dx. And the good news is that this integral here can now be found analytically. So we are looking at minus 16x over 9 e to the minus 3x plus 16 over 9 times minus a third e to the minus 3x. I'm not putting a constant of integration. It's not needed because I'll be applying the limits. So we've got minus 16x over 9 e to the minus 3x minus 16 over 27 e to the minus 3x. Now remember that this is this integral here. So going back to the expression for r, we had the minus 8 over 3x squared e to the minus 3x plus the expression we just obtained here. So let me put everything together. We've got that the region r is given by minus 8x squared over 3 e to the minus 3x minus 16x over 9 e to the minus 3x minus 16 over 27 e to the minus 3x with the limits being 0 and 1. I will now show the substitution of the upper limit and the lower limit. So if I substitute 1, we get minus 8 over 3 e to the negative 3 minus 16 over 9 e to the negative 3 minus 16 over 27 e to the negative 3. That's the upper limit substituted minus the lower limit, where the lower limit is 0. So these two terms will simply be 0 because of the x and the x squared term. So we've got 0 plus 0. And then we've got minus 16 over 27 e to the 0, which is simply minus 16 over 27. Now it's time to simplify things. We are looking at minus 136 over 27 e to the negative 3 plus 16 over 27, which is the final answer for the region R. In 12a, we need to express 1 over v, 25 minus v in partial fractions. So this is the original expression I've got, the original fraction. It's 1 over v, 25 minus v. So I'm proposing that these can be decomposed into a over v plus b over 25 minus v, where a and b are constants to be determined. So the LCM is v times 25 minus v. So if I multiply throughout by the LCM of v, 25 minus v, we get that 1 is a times 25 minus v plus bv. Now we know that this holds true for any value of v. So if I substitute v is equal to 0, I get that 1 is 25a, and therefore 1 over 25 is the value of a. And if I put v to be 25, we get that the 25 minus v is 0. So 1 is equal to 25b, and therefore 1 over 25 is the value of b. I still need to write the decomposed form. So we've got 1 over v times 25 minus v being equal to 1 over 25 over v plus 1 over 25 over 25 minus v. Now the volume capital V microliters of a plant cell T hours after the plant is watered is modeled by this differential equation. Now the plant cell had an initial volume of 20 microliters, and we need to find, according to the model, the time taken in minutes for the volume to reach 24 microliters. So I need to start by solving the differential equation here. And what I'm going to do, I'm going to use cross multiplication to separate the variables. So collect the v's with the v's on the left hand side and the remaining terms with the t on the right hand side. So we are looking at 1 over v times 25 minus v dv being equal to 1 over 10 dt. I can now integrate both sides, and I recognize on the left hand side the expression we decomposed into partial fractions in part A. So on the left hand side we are looking at the integral of 1 over 25 over v plus 1 over 25 over 25 minus v dv, and on the right hand side we've got 1 over 10t plus c. I just integrated. Now let's do the integral on the left hand side. The integral of 1 over 25 over v is simply 1 over 25 ln of the absolute value of v, and then the integral of 1 over 25 over 25 minus v, it's going to be minus 1 over 25 ln of the absolute value of 25 minus v. Now the negative sign is coming out of the derivative of 25 minus v, which is negative 1, and all of this is equal to 1 over 10t plus c. Now I'll be using the fact that when t is 0, v is 20, so that I can find the value of the constant c. This means that we've got 1 over 25 ln of 20 minus 1 over 25 ln of 25 minus 20 is equal to 0 plus c. So 1 over 25 ln of 20 minus 1 over 25 ln of 5 is equal to c. So we know that when we've got subtraction of two logarithms, then I do the logarithm of the division of the quotient. 20 over 5 is 4. So we've got 1 over 25 ln of 4 to be the value of c. And this means that the model is 1 over 25 ln of the absolute value of v minus 1 over 25 ln of the absolute value of 25 minus v is equal to 1 over 10t plus 1 over 25 ln 4. Now I'm trying to find the value of t when v is 24. So when v is equal to 24, then we're looking at 1 over 25 ln of 24 minus 1 over 25 ln of 25 minus 24 is equal to 1 over 10 t plus 1 over 25 ln of 4. Now 25 minus 24 is simply 1, and the ln of 1 is 0. So I'm looking at 1 over 25 ln of 24 minus 1 over 25 ln of 4 being equal to 1 over 10 t. Once more, I'll be doing 24 divided by 4. This means we've got 1 over 25 ln 6 to be equal to 1 over 10 t. And if I cross multiply, I get 10 over 25 ln 6 to be the value of t. So let me go on my calculator. 10 over 25 ln of 6. This is the value of t. So t is equal to 0.7167 ... Remember, t is the number of hours. We're asked to give the time in minutes, so I will simply press the button below the square root. This will convert the decimal into hours and minutes and so on. We're looking at 43 minutes 0 seconds, so we conclude that the time taken to reach a volume of 24 microliters, it's gonna be 43 minutes. In part C, we need to show that capital V is A over e to the minus kt plus b, where a, b, and k are constants to be found. So essentially, we need to consider the solution we obtained in part B and solve for v. So I will start by multiplying throughout by 25 to get ln v minus ln of 25 minus v being equal to 5 over 2t plus ln 4. I will be collecting all the ln's on the right hand side. I'll be moving the 5 over 2t over the left hand side. This will give me negative 5 over 2t on the left hand side, which seems to agree with the fact that the power here is negative. So I've got minus 5 over 2t is equal to ln 4 minus ln v plus ln of 25 minus v. Now I can combine the right hand side into a single logarithm. The addition here will mean that I'm multiplying 4 with 25 minus v, and the subtraction here means I'm dividing by v. So all in all, we are left with minus 5 over 2t being equal to a ln of 4 times 25 minus v, and all of it divided by v. So I will remove the ln by taking e of the left hand side. So e to the minus 5 over 2t is equal to 4 times 25 minus v, and all divided by v. I will then proceed by expanding the right hand side. So e to the 5 over 2t is 100 minus 4v over v. This can be written as 100 over v minus 4v over v, which of course simplifies to 100 over v minus 4. So I'll move the negative 4 over the left hand side. So 4 plus e to the minus 5 over 2t is equal to 100 over v. And then I can flip both sides. We're looking at 1 over 4 plus e to the minus 5 over 2t is equal to v over 100. And then I can cross multiply the 100 here to isolate the v. So we're looking at 100 over e to the minus 5 over 2t plus 4 is equal to v. The model predicts that there's an upper limit capital L microliters on the volume of the plant cell, and we need to find the value of capital L, giving a reason for our answer. So I will be considering what happens to capital V as t grows larger and larger. So as t goes to infinity, as t tends to infinity, the e to the minus 5 over 2t tends to 0. So we are looking here essentially at 100 over 4. So I'm going to write here that v tends to 100 over 0 plus 4, which is equal to 25. And therefore we conclude that capital L is 25. However, if we cannot see the limiting process here, what I can do is go on my calculator, substitute a big number on my answer key, something like that, and then I'm gonna do 100 over the e to the minus 5 over 2 times the ans. So I'm mimicking the process of t growing larger and larger plus 4. I press the equal sign, I see the 25, so capital L is 25. In question 13, we're modeling the world human population capital P billions through this equation here. Capital P is A, B to the T, where T is the number of years after 2004. Now using the estimated population figures for 2004 up to 2007, a graph of log P base 10 is plotted against the T, and the points lie approximately on a straight line with a gradient of 0.0054 and an intercept of 0.81 on the vertical axis. And we need to estimate to 3 decimal places the value of A and the value of B. So based on the information here, the gradient and the intercept, we can start by saying that log of P base 10 is equal to 0.0054t plus the intercept of 0.81. This is the equation of the straight line of log P against T. Now taking the original model, which says that P is A, B to the T, I can take log of both sides. So we're looking at log of P base 10 being equal to log of A, B to the T base 10. So we've got log of P base 10 is equal to log of A base 10 plus log of B to the power of T base 10. And I can now use the power law of logarithms to say that log of P base 10 is equal to log of A base 10 plus T log of B base 10. I will then proceed by comparing the original equation of the straight line with this one here, and we can see that the 0.0054, the gradient of the straight line, corresponds to log of B base 10. It's the coefficient of T, and the intercept of 0.81 is the log of A base 10, and therefore we are looking at log of B base 10 being equal to 0.0054, and then log of a base 10 being equal to 0.81, which means that b is equal to 10 to the power of 0.0054. If I plug this on the calculator, I get an answer of 1.013, and then a is 10 to the 0.81, and this gives an answer of 6.457. In part B, we're asked to interpret the values of a and b in the context of the model. Well, the model said that capital P is AB to the T, and we found this to be 6.457 times 1.013 to the power of T. Now, for the value of A, we observe that if we substitute T is 0, we get that capital P is 6.457, which means that the initial population, it's the population in 2004, was 6.457 billions. And then we can see that the 1.013 is the multiplying factor, because every time that the T increases by 1, so every year we multiply by 1.013, and we know that the multiplying factor of 1.013 corresponds to an increase by 1.3%, and therefore each year the world human population increases by 1.3%. In part C, we need to use a model to estimate the world human population in 2030. Now we know that the initial population was at 2004, that's when T is 0. So for 2030, this simply means that T is 26, and therefore we've got that P is equal to 6.457 times 1.013 raised to the power of 26. This gives an answer for capital P of 9.034, and therefore we conclude that the population in 2030 is going to be 9.034 billions. I need to include the billions here to claim both marks. In D, we need to comment on the reliability of the answer to part C. Now in part C, we estimated the population in 2030. However, we were told that the model was based on the years 2004 to 2007, and therefore we conclude that this is unreliable because 2030 lies outside the range of observed data. In question 14, we've got the circle C1 here, and we need to find the coordinates of the center and the radius of this circle. Well, let's start by reminding ourselves that the circle with center alpha, beta, and radius r has this equation here. So I'll be completing the square here in order to put it in the standard form and read off the coordinates of the center and the radius. So first of all, we're looking at x squared minus 6x plus y squared plus 14y plus 33 is equal to 0. So we've got x minus 3 squared minus 3 squared plus y plus 7 squared minus 7 squared plus 33 is equal to 0. So we're looking at x minus 3 squared minus 9 plus y plus 7 squared minus 49 plus 33 is equal to 0. So we've got x minus 3 squared plus y plus 7 squared minus 25 is equal to 0, taking me to x minus 3 squared plus y plus 7 squared being equal to 25, and therefore we conclude that the center of the circle C1 has coordinates 3, -7, and the radius r is the square root of 25, which is simply 5. We're then given a different circle C2 with center being -6, -8, having radius k, where k is a constant. Now we are told that the two circles C1 and C2 are intersecting at two distinct points, and we need to find the range of values of k, writing our answer in set notation. Now before proceeding and doing any calculations, let's go on Desmos to see exactly what's happening. So here we've got circle C1 centered at B and circle C2 centered at A. Now we can vary the radius of the circle appearing in blue, the circle C2, and we can see that as we increase k, we've got two distinct points of intersection. Let me put the animation on. we've got exactly no points of intersection, 1, then 2, 2, 2, and then again 1, and then 0. So we can see that there are two critical values. The moment the circle C2 is touching the outside of the circle C1, and then the moment that C2 is touching the left hand side of the circle C1. These are the two critical values for K. Anything in between will ensure two distinct points of intersection between the two circles. We can therefore proceed into sketching the situation here. We've got the circle C2 centered at 3, -7, having a radius of 5. We've got the circle C1 here. This is the first critical value where the two circles are tangential on the left hand side. And then if I open up the radius of C1, we've got the second critical value at which point C1 is tangential to C2 on the right hand side as shown. Now it is crucial now to determine the distance between A and B. So the distance AB, I'm going to use the distance formula. We're looking at -7 minus the -8 squared plus the 3 minus the -6 squared and all square rooted. Now if I evaluate this, I get an answer of √82, which is the distance between the two centers. So let me write this down. √82 is the distance between A and B. And we can see that the first critical value for K is when K is exactly this distance here, which is √82 minus the radius of 5. So let me write this down. This distance here is going to be √82 minus 5. And the second critical value for K will be when K is equal to this distance here, which is the √82 plus the radius of 5. So let me write this down. This distance here, it's going to be √82 plus 5. So anything in between these two critical values is enough to guarantee that we've got two distinct points of intersection. Now we've been asked to give our answer in set notation. So my final answer here will be all K such that K belongs to the reals, and we've got √82 minus 5 being less than K being less than √82 plus 5. Obviously, we need strict inequalities because we've got two distinct points of intersection. If we are equal to the critical values, then we've got a single point of intersection. So this is the final answer for part B. In question 15, we're given the equation for curve C, and we're asked to find an expression for dy dx in terms of x and y. Now I'll be using implicit differentiation here, which means I differentiate from left to right. We apply all rules of differentiation as usual. If we happen to be differentiating a term in y, we put the dy dx term as well. So the derivative of x plus y to the power of 3 will be getting the power down, deducting 1 from the power times the derivative of the bracket. Well, the bracket is x plus y, so it's going to be 1 plus dy by dx, and this is equal to 6x minus 3 dy dx, and the -2 vanishes because it's a constant. I will proceed by dividing throughout by 3 to get x plus y to the power of 2 times 1 plus dy dx being equal to 2x minus dy dx, and then I will expand the left hand side to get x plus y squared plus x plus y squared times dy by dx being equal to 2x minus dy dx. I will be collecting the dy dx terms on the left hand side, taking me to x plus y squared dy dx plus the dy dx being equal to 2x minus the x plus y squared. Now we've got a common factor of dy dx on the left hand side, so we've got dy dx times x plus y squared plus 1 being equal to 2x minus brackets x plus y squared, and therefore we conclude that dy by dx is equal to 2x minus the brackets x plus y squared, and all divided by x plus y to the power of 2 plus 1. Now the point P with coordinates 1, 0 lies on C, and we need to show that the normal to C at P has equation y is -2x plus 2. So I will start by substituting x is 1 and y is 0 into the expression we obtained for dy dx in part A. So dy dx in this case, it's going to be equal to 2 times 1 minus 1 plus 0 to the power of 2 over 1 plus 0 to the power of 2 plus 1. This gives an answer of a half, and therefore we can conclude that the gradient of the normal will be found by flipping and changing the sign of the gradient of the tangent. So it's going to be negative 2. And we can proceed with y minus y1 being equal to mx minus x1, taking us to y minus 0 being equal to negative 2x minus 1, and therefore y is equal to negative 2x plus 2 as required. In part C, we need to prove that the normal to C at P does not meet C again, and we need to use algebra for this proof and make the reasoning clear. So essentially, we're looking at the solution of two simultaneous equations, the equation of the normal and the equation of the curve. So I'll be substituting y is negative 2x plus 2 into the equation of the curve. So we're looking at x plus the negative 2x plus 2 to the power of 3, and this is equal to 3x squared minus 3 times the negative 2x plus 2 minus 2. I will proceed by expanding the bracket here, so we're looking at x minus 2x plus 2 to the power of 3 being equal to 3x squared plus 6x minus 6 minus 2. So we're looking at 2 minus x to the power of 3 being equal to 3x squared plus 6x minus 8. I will then expand the 2 minus x to the power of 3, and I can use the binomial expansion here. So we've got 2 to the power of 3 plus 3 choose 1, 2 to the power of 2 times the negative x plus 3 choose 2 times 2 to the power of 1 times negative x squared plus the negative x cubed being equal to 3x squared plus 6x minus 8. Alternatively, you just expand 2 minus x times 2 minus x times 2 minus x. It will surely lead to the same answer. So on the left hand side, we've got 8 minus 12x plus 6x squared minus x cubed being equal to 3x squared plus 6x minus 8. I can collect everything on the left hand side, taking me to 0 being equal to x cubed minus 3x squared plus 18x minus 16. I've been investigating solutions of this cubic here, but since we're asked to use algebra, we cannot use the calculator to solve the cubic here. Instead, let's consider that we already know that P being a point on the curve means we know that x is 1 is a solution, and therefore x minus 1 is a factor. So I can proceed with the long division. So I'm dividing x cubed minus 3x squared plus 18x minus 16 with x minus 1. So the first thing I write is an x squared term here. So I've got x cubed minus x squared, and I'm deducting. This leads to minus 2x squared plus 18x minus 16. So I need a minus 2x here, taking me to minus 2x squared plus 2x. I deduct again, and I get 16x minus 16. So a plus 16 here will give me 16x minus 16. And if I deduct again, I get the result of 0 as expected. This simply means that we are looking at x minus 1 times x squared minus 2x plus 16 being equal to 0. And therefore, we either have that x minus 1 is 0, or alternatively, we're looking at x squared minus 2x plus 16 is equal to 0. Now, the solution of x being equal to 1 corresponds to the point P, and we are asked to show that the normal and the curve will never meet again. So I expect this quadratic not to have any real solutions. And to show this, I need to consider the discriminant. So the discriminant is b squared minus 4ac. So in this case, it's going to be negative 2 squared minus 4 times 1 times 16. This gives an answer of negative 60, which is less than 0. And therefore, we conclude that we've got no solutions from the quadratic here. So the only solution is the point P, which simply means that the normal to C at P does not meet C again. We need the conclusion here to claim full marks for this part of the question.